Hello everyone. I hope I am audible, guys. If you can hear me, please give a thumbs up. If I am visible and I am audible, please give a thumbs up. Hmm. Hi Meet, can you hear me? Uh, Guys, can you see me? Guys, am I audible, guys? Looks like no. Hello guys, can you see me or hear me? Anyone? Please give a thumbs up if you can hear me. Hi Varun, hi Ashwin. Please give a thumbs up if you guys can see me or hear me. Sure, thanks Ashwin. Yeah. Okay, so guys, this is Himanshu. I recently graduated from IIT BHU. In college, I was mostly involved in competitive programming. I started in my end of my first semester, and I participated in lots of Code Forces contests and prepared for interviews. And I mean, it's almost all the journey that usually people go through. I mean, I also participated in ICPC regionals and all. So yeah, so maybe I have a lot to share. But today we are going to discuss some basic standard number theory concepts. So today we are going to discuss prime numbers and sieve. So these are pretty basic concepts. You must have heard of them, but the logic behind them is pretty simple. I hope you guys get to understand about it in this session. So yeah, so we can start with that. Yeah, yeah, sure. So let us let us begin with what are prime numbers. I mean you all must know, but what are prime numbers? The prime numbers are just basically all the numbers which are only divisible by 1 and itself. That's just the pretty basic definition. You don't need to remember anything else. It's just numbers divisible by 1 and itself. Let's begin with this. It's just that the numbers which are divisible by 1 and itself, and nothing else. That's all. Those are prime numbers. And what is the opposite of prime numbers? These are composite numbers. So composite numbers, what are those? They have at least one number other than 1 and itself divides it. That is all. These are prime numbers. We have only 1 and itself dividing it. For composite numbers, we have at least one other number that divides the number apart from 1 and itself. So I mean, let me give you some basic examples. Examples we have is 7 is prime. Why? Because no number divides 7 except 1 and 7. But 12 is not. Why? Because apart from 1 and 12, we have 2 dividing 12, 3 dividing 12, 4 dividing 12, 6 dividing 12, and lots of other numbers. But we just only want at least one number to divide it. So 12 is not prime. It's composite. Yeah. So let's say talk about 77. Is 77 a prime number? No, because we have 7 dividing it, we have 11 dividing it, so it is not a prime. So you see, it's pretty easy if you have small numbers, right? Because you can do hit and trial method and check if there exists a number that divides the number apart from 1 and itself. So for small numbers it's pretty easy, like you can do it by hand and hit and trial method. So that is easy. But for bigger numbers, like let's say I am saying, what about 8967? Can you tell me if it is a prime or not? So that's a bigger question. So we will see how we can, I mean, we will see the approaches that we can check whether a number is prime or not. So let us start with the definition of the prime that we had. Prime is divisible by only one n itself. So what we should try to do is, we should try to find any number that divides any number and check whether that number is divisible by that or not. Let's say we have a number n. So we want to check if this is prime or not. N is prime or not? N is prime. So what we are going to do is, apart from 1 and n, we are going to check if someone divides it. That is all we want to check. We want to check if a number apart from 1 and n divides the n. So what we can do is, we can check from all numbers 2, 3, 4, ... We can check up to n minus 1, because n, we know that n is going to divide n, and we have to remove that from the definition. So we just have to check if any of these divides n or not. So that's pretty simple. Like, we can simply, this is a brute force solution. We can simply iterate from number from 2 to n minus 1, and we just simply check whether if n is divisible by num. So when n is divisible by num, the remainder we would get is 0, right? So if n after dividing from num gives remainder 0, it means it is divisible by num. So it means that n is composite. Okay, so we get n is composite. Let's say that we have is prime, is n prime, let's say. Currently we are assuming that yes, it is prime. So let us assume that it is prime at any point of time when we are able to find a number other than 1 and n. So that is already covered. Why? Because we are iterating from 2 to n minus 1 only. So if at any point of time we find that there is a number that divides n, then we say that n is composite, n is not prime. So we check, we say that is n prime? No. Oh, okay. Guys, yeah. Okay, let me check. I didn't share the screen, I think. Yeah. Sorry, yeah. Guys, can you see the screen, guys? Oh, sorry, Sangeeta. Yeah, yeah, I missed that. Yeah, there's a lot of setup. Yeah. So, guys, is the screen visible now? I can iterate through that again. Sure. Yes, yeah, sure. Thanks, Mohit. So, this is the standard definition of prime: numbers divisible by 1 and itself and nothing else, right? And opposite are the composite numbers. At least one number other than 1 and itself divides it. That's all. That's all one remembers about prime, and that's all one should remember too. And some examples, like 7 is prime because nothing else divides 7 except 1 and 7. 12 is not prime because we have 2, 3, 4, 6, etc. dividing 12. 77 is also not prime because we have 7 and 11 that divide 77 apart from 1 and 77. So from now on, I'm not going to say apart from 1 and n because we know that's implicit. So yeah. So for bigger numbers, it becomes a problem. Like, how do we check? So like, we cannot check from hand. So I mean, we can use help of code. Yeah. So how the standard way that, I mean, anyone can check whether n is prime or not is that he can simply try from 2, 3, 4 up to n minus 1 and check whether any of them divides n. If we get a number which divides n, then we know that n is not a prime. Why? Because it's the standard definition. So initially we assume that n is prime. Okay. And now we are going to search for a number which divides n or not. So what we do is we iterate from all the numbers 2 to n minus 1 and just simply check if n after division from the number gives a remainder 0. That means it's divisible. So if we get a number, then we say that n is composite, and is n prime is false. Yeah, because it's not prime. So yeah. So in the end, we can simply check if is n prime, then we can say that yeah, n is prime. N is prime. Yeah. So this is a pretty basic approach to, you know, determine if a number is prime or not. Like, even if somebody gives you the definition of this, This is the first thing that you can come up with. You just simply check if any number divides it or not. That is all. Okay, so what about the how much time does it take? So that's time complexity, right? So how much time does it take to check whether a number is prime or not? We have to do n operations around. We have to do n operations. By operation I mean this check of remainder, right? Because for every number we are going to check if it is divisible. So we do n operations. So time complexity is order of n. So this means that we are not going to check manually, right? Because let's say I give you a number 10 power 8 of order 10 power 8. So you are not going to do manually. You are going to have computer do it. So when computer does it, so we have a limit on the speed that computer can do. So that is around 10 to the power 8 operations per second, I guess. Yeah. I assume that I take this one and I analyze the time complexity and the number of operations, assuming that the computer can do 10 to the power 8 operations per second. That is in C++. That is very important. In C++, a computer can do 10 to the power 8 operations per second. So you can do all of your analysis, like whether my solution is fast enough or not, by checking that how many operations does my code do at max, right? And if it's greater than 10 to the power 8 operations per second, this is important, per second, then it probably will get time limit exceeded. So cool. So our time complexity is order of n, right? So this means that and since we can do 10 to the power 8 operations per second, so for numbers up to 10 to the power 8, we can check prime or not in 1 second, right? In 1 second. Yeah, for numbers up to 10 to the power 8, we can check prime or not in 1 second. Why is this 1 second important? Because usually the codes that you write in the interviews and in the code forces rounds, in the CodeChef rounds, generally they are the time limit is like 1 to 10 seconds max, I guess. Yeah, that is the maximum range I have seen. It can be 0.5 also. So I have seen time limits from 0.5 to 10 seconds. So that is why this 1 second is important. If you have a lot of time, then you can definitely check numbers up to, bigger numbers using this approach. Yeah, but usually we have this. So we are going to consider time limits around this one, 0.5 to 10 seconds. Cool. So this is how we are going to, we can check whether a number is prime or not. If the number is up to 10 to the power 8, for bigger numbers, we are going to be needing much more time, right? Because we have to go through a lot of numbers and check whether number is divisible or not, right? This is the brute force approach. I hope it's clear, and let's see if you guys have any questions. Sure, screen is visible. No questions yet, guys. If you have any questions, please definitely ask them. Yeah. So this was the pretty basic one, the basic approach. Now we are going to see. Now we are going to analyze this thing, like what we have done here. So this is something. This has something magical in it. I'm gonna say, yeah. Why? Because let us find what is so interesting about this. Actually, currently we don't have anything interesting. We can make it interesting. How? We simply break from here. Why? Break because we got one number which divides n, and we just need only one number for the primality test, right? Because we just want to check whether at least one number exists which divides n, right? So as soon as we get a number which divides n, we are going to break out of the loop. Why do we have to check other numbers? Because we already know that the number is not prime, it is composite. So we simply break out of it. So even if you are doing it manually also, let's say we are checking for 14. 21. Let's say we are doing for 21. So we check for 2. 21 is not divisible by 2. We check for 3. 21 is divisible by 3. So we simply stop at 3. No sane person would go and check for 4 and 5 and 6, right? Because we got 3, so we will stop there. So this part is important. So now let us analyze why is this interesting. Let us say that we have let us try a dry run on some numbers. Let's say we dry run it on 77. Okay, let's check whether 77 is prime or not. So we check by 2, not divisible. We check by 3, not divisible. we check by 4, not divisible, 5 not divisible, 6 not divisible, 7, yes, it's divisible by 7. Yes, it's divisible by 7, so we break. So I was saying that we do our operations of around order of n, but you see that we did only 6 operations. We did only 6 operations, not 77. But you can say that it's just because in case of 77 we got the number pretty quickly. Let's see, what's the guarantee that we generally break out of the loop very soon, right? So you can argue that, yeah. So let us take some bigger numbers. Let's take 143. Okay, so we divide by 2, not divisible. We divide by 3, is it divisible? No, not divisible. Divide by 4, not divisible, I think, yeah. 5 not divisible, 6 not divisible, 7, is it? No, not. 8's not. 9, no. 10, no. 11, yeah, it's divisible by 11. Yes, it's divisible by 11. So we did 10 operations. I mean, still we don't get to see like it's of order 143 and we are doing only 10 operations. So it's still a big difference, right? So you can do case analysis and you can start seeing that it's a bit of a pattern. What's the pattern is that the pattern is only for composite numbers. So it is going to help you if the numbers are composite. So how is it going to help you? I'm going to write a statement here. Before writing that statement, I want to say one thing. Yeah. Let us analyze this in case the number n is not prime. So what will happen is, when will this loop break? I'm saying that n is not prime, it is composite. So when is this loop going to break? When this num becomes equal to smallest prime divisor of n. Yeah, that is a big statement, but yeah, it's a useful one. Loop breaks when num equals smallest prime factor of n. SPF is the smallest prime factor of n. Why? Because we are iterating from smallest to lowest, right? So we'll gradually check for 2, 3, 4 and 5, and as soon as we get the smallest prime divisor of n, we simply break out of the loop because it's a divisor, so remainder would be 0, right? So this is a important thing. I mean, analyzing this when this loop breaks in terms of the prime factors. So what it says is that this loop is going to break. This loop is going to run for smallest prime divisor of n operations. So what I can say is the time complexity if n is composite is SPF of n, because we know that we are not going to do n operations. We are going to do only the operations equal to smallest prime factor of n. We can check that here. For 77, how many operations did we do? 6, and 6 and 7, they are definitely close enough. For 143, we have, this is 11 into 33, right? So yeah, I hope it's 11 into 33. It's 11 into 13, yeah. So smallest prime factor is 11, and how many operations did we do? We did 10 operations, and 10 and 11 are close. So if you want to know exactly, that's the thing. Exactly, smallest prime factor number of operations are going to be taken up. Now, special thing about this is that for composite numbers, let's say p is the smallest prime factor. P is the smallest prime factor. So what it means is that p and the remaining part x, that is going to make n, right? Because it is composite and p is the smallest prime factor. So apart from p, there must be something. If there is nothing, then it cannot be composite, right? Because x cannot be equals to 1, because then n would be a prime, because p is prime. So x must be something greater than 1. I'm talking just about the composite numbers. So we have p into x is equals to n. Now one thing we can check for that is p must be less than equals to x. Why? Because p is the smallest prime divisor, right? X is also a divisor of n. What does this statement tell you? P and x both are divisor, both divide n. And why p is less than equals to x? P is the smallest. We already said that. And the loop also breaks on the smallest prime divisor only, so we know that. So p is less than equals to x. So can we somehow get a bound? Like what we can do is, we can do it, we can multiply p on both sides. So what does that give you? P into x is equals to n. So we can write it like p into p is less than equals to n. So p is less than equals to root n. This is a bound that you many of you guys have heard also. So I mean, this is one way you can look why root n works. That's because the main part is composite numbers. Every composite number's smallest divisor is less than root n. This is a statement. You can you can keep it that way, because for every composite number means we have at least two divisors, different divisors. So the smallest one of them must be definitely less than root n. Why? Because both of them cannot be greater than root n. If both of them are greater than root n, then the product would be greater than n, but it has to be equals to n, right? So what I mean to say is that a into b is equals to n, right? So both of them cannot be greater than root n. Both of them cannot be greater than root n at the same time, because the product would be greater than n at that time, and that this equation would not hold. So what I can say about is minimum of a comma b, that would be definitely less than equals to root n. Yeah, so this is how the root n comes into play. So so how does this help us? This helps us not in case of primes, but in case of composites. So what we can do is we would try to check whether it is a composite number or not. So what we could do is we could try to check for all possible numbers up to root n only, not up to n. Why? Because if it is composite, we would get a prime divisor up to root n at max, and if we don't get up to root n, we are not going to get it later also. Why? Because let's take a composite number 77 only. Yeah. So what is 77's root is 9, I guess. We can take 9. Yeah. Square root is 9. So what I'm going to do is I'm going to check for 2, 3, 4, 5, 6, 7, 8 and 9. That is all. I'm going to check for them. So let's check for 2, no, 3, no, 4, no, 5, not divisible, 6, not divisible, 7 divisible. So we got it. Let's take a prime number. Let's take 31. Let's say 31. Yeah. Let's say 43. So what's the square root of 43? It would be around 7. Yeah, 7 square is 49. So yeah, that's a good bound. Yeah. So I'm going to check for 2, 3, 4, 5, 6, 7. Yeah. I'm going to check for this. 2 does it divide? No. 3 does not divide. 4 no. 5 no. 6 no. 7 no. But you can say that why didn't we check for 8, 9 and up to all the elements, right? That is not possible. Why? Because if something bigger divides, then something smaller must also divide. Why? Because if a is bigger, then correspondingly b would be less than root n. So we already have checked for less than root n values. So there must have existed another value from this range, right? So if a number from this range does not exist, it guarantees that a number from this range also does not exist. So that is why this helps us in case we want to check for whether numbers are composite or not. And by contradicting property, we can say that if numbers are not composite, they are prime. So that is how we can check for primes also in root n. So what we do in the case of brute force, we just check. We know that we don't need to go over up to n. We have to go up to root n only, because if the number is composite, we would definitely get a prime divisor up to here only if the number is composite. Otherwise the number is not composite, hence it's prime. So this is going to change like is n composite, and we are going to say that it's not, and we are going to check that if we get a prime divisor from 2 to root n, we say that n is composite and is n composite equals true. Yes, this time we are checking for composite, and if it's not composite, then we say that if n is composite, then we say that it's not composite, hence this must be prime. Sure. Yeah. If n is composite, if not, then we can say that n is prime. So we have two things, primes and composite numbers. So in this case, we try to check for composite numbers, and we check whether a prime divisor exists or not. And since we know that if a prime divisor existed, it must have been less than root n. So that is why we go up to root n only, right? So yeah, or you can also you can also remember one thing that would help you in such problems is that divisors always exist in pair, right? Because let's say if d divides n, there is a divisor d of n, then n by d is also a divisor of n, right? So divisors always come in pairs. D is divisor, and so n by d would also be a divisor, is also a divisor, right? That's pretty trivial. So but yeah, I'd like you to remember that if d is a divisor, n by d is also a divisor, they come in pairs. So yeah, just like here, if a is a divisor, then b is also a divisor. Yeah, so this is how we can check whether a number is composite or not, prime or not, in order of root n. So yeah, so I mean, if we are writing code, it's pretty much just 2 lines of code. Yeah, I mean, we can check, we can write is prime. We can write code also. It's nothing. We can test it. Let me see if you guys have any questions. Yeah, there is one question. I think it's for one test file. Yeah. No, I mean, Rohit, in CodeChef problems, if you have problems and they say that there are test cases, then although test cases are present in a single file only, they have multiple files also, but for one file you have that limit. That limit is for one file, not for each test case. The test cases mentioned in the problem, all of them have to be solved within the given time limit, 0.5 to 10, whatever it is. It's not that there are 100 test cases in one file, so we get 10,000 seconds, 1000 seconds. That's not it. Rohit also asks why loop only breaks when we get smallest prime divisor. Why can't we say only smallest divisor? Yes, that's a good question. Yeah, I would say this is for conceptual point of view, this is a very good question. So he says it should be a smallest divisor. Loop breaks when we get a smallest divisor. So smallest divisor and smallest prime divisor, these are the same thing. Why? Because let's say we have a smallest divisor and it's not a prime. What I'm trying to say is that smallest divisor will always be a prime. So let me show you how. If a smallest divisor is not a prime, then it means it is a composite number, and since it is composite, it can be broken into even smaller primes, right? Because every composite number can be decomposed into primes. What is the benefit of primes? We can divide every composite number into prime factors, and that's very powerful stuff. I mean, we can use that to do lots of things, like, I mean, we can see in later sections. So if it is not prime, that means it is composite, and if it is composite, we can divide it into smaller primes. And if the bigger number was dividing n, then the smaller numbers would also divide n, right? Let's say that it was p1 into p2, and we say that p1 into p2 was the smallest divisor. It was the smallest divisor of n, but that cannot happen. You can see because p1 into p2 cannot be smallest divisor, because the smallest divisor is minimum of p1 p2, right? Because this is composite number, it can be broken into smaller primes, and those primes also divide n, right? Because if p1 p2 divides n, p1 also divides n, p2 also divides n. Let's say, take example, let's say we have 6. Let's say we have 6 divides n. 6 divides 12, but 6 cannot be the smallest divisor of 12. Why? Because 6 can be decomposed into 2 into 3, and 2 also divides 12 and 3 also divides 12. Therefore smallest divisor must be prime. Therefore our statement that 6 is the smallest divisor of 12, that is wrong. So our assumption is wrong. So smallest divisor is always the smallest prime divisor. I hope, Rohit, that's clear. Smallest divisor is always a prime divisor, because if it is not, we can get a even smaller number, right? Yeah. Okay, so that's about checking the numbers whether they are primes or not in root n. So let us write about the time complexity. What time complexity is? Time complexity is order of root n. Yeah. So how much can we how big numbers can we check from this? So we can do 10 power 8 operations, right? So that means we can check for numbers up to 10 power 16. Numbers up to 10 power 16 can be checked whether they are prime or not, because they would take 10 power 8 operations. Root of 10 power 16 is 10 power 8. So now we can check numbers up to 10 power 16 in 1 second. Numbers up to 10 power 16 range in 1 seconds. Yeah, that's a big leap. Yeah, 10 power 16 number is pretty huge. Yeah. So yeah, so now we can move on to I mean, this was checking whether a number is prime or not. We can move on to finding primes even faster way. So we can move on to the next topic if you guys don't have any questions. Yeah, thanks Rohit. Yeah, this is number theory for competitive programming, Yogesh. Basics of number theory, checking primes and finding primes. Yeah, so now we will be going ahead with finding primes. Did I? Oh, I did not code this one. So let us code this first. So we have a number. We are going to check if it is prime or not. So we are going to check if it is composite or not. Is composite. So currently we say that it is not composite because we did not find any number yet which divides n. Now what I'm going to do is I iterate from 2 to n minus 1 and I check. Oh, not n minus 1, it's square root of n. So square root is equals to I don't want to use square root. Maybe we can use square root of n, and I go up to s I plus plus, and I simply check if n is divisible by this I. Let's call it num that we had in the present. Yeah, if n is divisible by num, it means that we got a number that divides n. It's composite, so we are going to break. We can simply return, return true. Return is composite equals to true. It's composite and we return true. Otherwise it's not composite, so that we already have. So we can simply return that return true, that it is a prime, is prime. Yeah, that is all. We just this is the main 2 lines of code that we check whether number exists or not. If we found number, we can at that instant only we can say that it's a composite number. So okay, so this checks for prime. So we say that this is checking for prime now. So this is composite is true, but prime it is not a prime. So we say that return false. Yeah, is not prime. Cool. Yeah, because we checked for composite. Yeah, it's not prime. And then in the end, if we don't find any number which divides it, we say that it's true, it's a prime number. That's all. We can it's fine, let's not run it right now. We can go ahead with with the Sieve part. Yeah, sure. Okay, no, not this. Yeah, so this was let me summarize a bit like what we had done. So let's start in the next page. Yeah, so what we did was checked primes in root n. One major takeaway I would say is that composite numbers have smallest divisors less than root n. This is a takeaway. Yeah, maybe. Yeah, composite numbers have smallest divisors less than root n. Smallest divisor less than root n. Cool. So now we can go ahead with how we can find the primes. Like let us say that I want to find prime numbers. Let's say I want to find primes. I want to find which of these are primes. Like let's say I have been given a set of numbers. Let's say we have lots of elements. Let's say we have 10 power 5 order elements, 10 power 5 elements as big as 10 power 6. Okay, so let's say that we have n elements. So what I'm trying to say is that it's not just only one element that we have to check for. Now we have n elements and we have to check which of them are prime. So we have to check which of them are prime, check which are prime, right? So we have n elements and we need to check which of them are prime. So how, we can use that approach that we learned. Let us do that. Sure. So for every element, what we are going to do is we are going to call this function is prime. So how much time does it take? Root n, we know that already, yeah. And since elements are up to 10 power 6, so it can take at max 10 power 3 operations, right? Because root 10 power 6 is 10 power 3. And we have, this 10 power 3 is being done for every element, right? In the worst case, let's say that we got pretty big numbers for all of them. So we know that numbers are up to 10 power 6. We would be needing only 1000 operations at max, and the number of elements can be up to 10 power 5, right? So this is the total max number of operations that we would be needing. This is 10 power 8. Sounds good. Works in 1 second. That's good. Yeah. This we can use that approach and do that in 1 second. Sure. So now let us say that we increase this. We increase this up to 10 to the power 7. We increase this up to 10 power 7. Yeah. So now how much time would be needing is 10 to the power. Let's keep this. Sure, 10 power 7 works fine. Yeah. So for a number as big as 10 power 7, how much time would we need to check if it is prime? That's 10 power 7 by 2, right? The square root 7 by 2. So let's simply write it as 3.5. Then how many numbers we have? This is pretty large, like 10 power 7 elements. Usually we don't get this much output, so let's make it a bit like we have in problems. 10 power 6. 10 power 7 is pretty big input output, so we usually don't have that in problems. So let's say that 10 power 6. So let's assume that in the worst case we have 10 power 6 elements, and every element is around this order, 10 power 7. So how much time we would be needing? That is 10 to the power 9.5. Doesn't seem to work, does not work in 1 second. In 1 second, and even how much time does it take? It would take around 30 seconds, I think. Would take 30 seconds. That's a lot, so would take 30 seconds around. Yeah. So we have to think of a better approach, this is not going to work. So what we are going to do is, what we can do is that we know that elements are as big as 10 power 7 only, right? So what we can do is we can check for all of the elements. We can find all of the primes beforehand. Let us try to do that. So instead of running a loop of around 10 power 3.5 for every element, we are going to check whether each for all elements from 1 to 10 power 7. For all elements from 1 to 10 power 7, let us calculate it beforehand only, right? This pre-calculation is very important in several problems. Like you can do lots of pre-calculations. Like in case of primes and divisors problems, you usually do lots of pre-computation and you answer queries. I have seen this a lot of times. Pre-computation is really helpful at places. So you know that if you know that the numbers can be up to 10 power 6 or 10 power 7, then definitely do pre-computation for all of them. Yeah. So let us try to find from 1 to 10 power 7 which of them are composite, which is prime. So our target is for every number from 1 to 10 power 7, let us target which is prime and not, and which is composite. Let us try to do that. So yeah, okay, cool. So okay, let's go back again to the definition of prime and composite. Prime divisible by only one in itself, composite divisible by other than that also, right? So let's say that we have a random number num. Then what can we say anything about its the multiples of num? Let's say numbers of the form num into x. Like what I'm trying to say is that if I have a number 6, then can we say anything about 12, 18, 30, 47, 42? Can we say about anything about these numbers? Since we know that these numbers already are divisible by 6, they can never be prime, right? So this time, instead of finding a number which divides the numbers one by one, like instead of going from 1 to 10 power 7 and checking whether each number is prime or not, what we can do is we can try and find a better approach where we can cancel out terms from our primes list. Like we can we can ignore some numbers which we are guaranteed that they won't be prime. For example, when we have 6, we know that all of its multiples are never going to be prime. Because why? Because they already have me as a divisor, right? 6. So all of its multiples, by multiples I mean not 6, I mean 6 is a multiple of 6, but I'm talking about multiples like 2, 3, 4x, not 1x, right? So all of its multiples, they already have me as a divisor, so I'm sure that they are not going to be primes. So what I'm trying to say is that all even numbers except 2 are composite, right? All even numbers except 2 are composite. So this way we reduce n by 2 numbers, and we just simply reduce n by 2 numbers, saying that they are definitely not prime. Why? Because they already are divisible by 2. So we simply I mean, without running that root and loop, we simply told all of them that you are not prime, definitely you are composite. So why just stop at even? We can say that all numbers multiples of 3 are composite. Sure, that's also true, because they have 3 as a divisor, right? So they cannot be prime. So instead of trying to find a divisor, what we are doing is we are fixing a divisor and saying that its multiples are composite. So earlier what we are doing is, in primes checking, what we are doing is we are trying to find a number which divides me. But here we have fixed that number and we are saying that all of the multiples are composite, they cannot be prime. So it's the other way around. So that's this is a better approach. I'll tell you where we are saving on this, like how is this better than the earlier one. So we can say that all numbers of multiples of 3 are composite. Why? Because they have except 3, of course, except 3, because they have me as a divisor. We can, why stop at 3? We can go on to 4 also. All numbers multiples of 4 are composite, right? Are composite. So yeah, so because they have 4 already as a divisor, right? So they cannot be prime because we already found one, and that is 4. So yeah, we can extend this up to as large as we want. So let's talk in I mean, this was this we were talking in, I mean, discussion sense, but let's talk in terms of how we are going to keep track of what is prime and what is not. So let us say that, I mean, it's important to think in terms of code as well, because I mean, in the end you have to write code, and if in the process of finding logic you think a bit about how the numbers are stored, what kind of variables you are going to keep, that is going to be helpful in implementation. So yeah, so, and that's also better to visualize also, right? Yeah, so let's check that. Let's make is prime array for all numbers 10 power 7 elements. Yeah, so is prime. What is prime? This is going to check whether is prime I tells if I is prime. 1 second guys, I'll be back once. Yeah, so what this array is going to tell is that if is prime I is going to tell if I is prime or not. If I is prime, okay, cool. So yeah, so this is the variable that we are going to maintain and pre-compute it. Okay, so the thing that we were going to do is, what we were thinking that all even numbers, by even we mean multiples of 2. So cross all multiples of 2. So what currently let us assume that all of them are prime. So set all to true. So this means that we are assuming that all of them are prime, and now we are going to cross out the composite numbers. So the composite numbers, how we can say, we are going to fix the divisor now, and we are going to iterate over the multiples, opposite of the other way that we were doing in the root and thing. So the first divisor that we are going to do is fix 2, then we are going to fix 3, then we are going to fix 4 and 5 and so on. So in case of 2, we are going to say 4, 6, 8, 12 in case of 2. So let's do it. Yeah. So 2 is going to cross 4, 6, 8, 10, 12. Yeah, so we are going to jump over the multiples and say that, hey, you are not prime, you are composite. And 3 is going to say that 6, 9, 12, to all of them that you are not prime, you are composite. Similarly, 4 is going to do that. 8, see that we are going at least 2x and not 1x. Okay. So 4, 8, 12, it's going to say that you are also not prime, you are composite. So we are going to say about 5, 10, 15, sorry, 10, 15, you are not composite, you are not prime, you are composite, and so on and so on. So how is this beneficial? That is, let's get that out. Yeah. So what we were doing in case of the earlier square root n1 is that whenever we were checking from all the numbers from 2 to n minus 1, what happened was, I'm going to take one example. Let's say we have 11 into 13. Okay. So this is a non-prime number. This is a composite number, and we would do around 10 operations that earlier we saw. So we are doing 10 operations. So the first 9 operations are getting wasted. 9 operations are getting wasted. Why? Because they did not divide it. They did not give me the result. Because 2, 3, 4, 5, 6, 7, they were just useless operations that I did, and they did not even divide 11. So that wasted my CPU cycles. You can say that wasted my time. I did 9 operations which did not tell me anything about whether the number was prime or not. What about this case? In this case, what we are saying is that every number is a candidate that can generate a result. So how? Because we can say that 2's multiples 4, 6, 8, 10, I am saying to them that they are not prime. So that's kind of a result. Like if you say something is prime or not prime, that means you are getting to some result point of view, right? Like here in this case, 11 into 13 was not divisible by 3. That doesn't give me anything. That doesn't tell me if it is a prime, if it is not a prime. So that's a wasted operation. But here, this has capability to tell whether 4, 6, 8, 10 is 4, 6, 8, 10, 12, these are prime or not, because it directly says you are not prime because I divide you. That's the main reason. You can say that 6 comes in 2 or in 3 both also. So that's fine. I mean, we can have repeated things, but definitely we can say that it's definitely better because there are no wasted operations. Like we don't have any operations that don't tell me anything, that are useless, like, because we are always giving the verdict, like 3 is saying to 12 we are not prime. So you can see these are only verdicts. So yeah, no waste operations. 3 is not saying that 12 you can be prime or not. Maybe, I don't know. 3 is not saying that. 3 is saying that you cannot be prime. Cool. So yeah. So let's see how much does this take. I mean, we don't know if this is even a efficient approach or not, because seems like in earlier cases we were running root n loops, and now we were iterating over multiples, and these multiples are getting iterated for every number 2, 3, 4, 5, 6, 7, 8, everything. So we're not even sure. Sure, Karthik. Yeah. So I'll check. So let's see whether let's see how efficient is this approach is. So I'll check that in a minute. Yeah. Yeah, Ravi. Yeah, that's a good observation. Yeah. So we will be getting onto that. Yeah. So yeah, before that, let's see whether this is efficient or not. Like, is this better than n root n thing? Like what in the root n case, what we were, these number of operations were getting used, 10 per 9.5. So this was the brute force one. Let's see if this approach even gives us less than 10 per 9.5 operations, because if it doesn't, then it's useless. Why do all this? Because we are not getting even less time complexity, right? So let's write the bit of a code. So yeah, this is known as Sieve. Like what is Sieve? Sieve is just iterating over multiples. So that's how I remember Sieve. It's just that you fix numbers and you iterate over their multiples. That is all. And I mean, it's also a 2-line code. Let's say that we have Sieve. We have Sieve here, and let's say for d is equals to 1, d is less than equals to n d plus plus. So this d is the number that d is the divisor that I'm going to fix. Sorry, so it should be 2. So this d is the divisor that I'm going to fix, and now I am going to jump over its multiples. That is all Sieve is, I mean, for me. So what I can say is, for int let's say num, and it must be at least 2 into d, because 1 into d we are not going to take. So at least 2 into d, num is less than equals to n. And since we are iterating over multiples, remember this is very important. I mean, maybe you have a typo or something, but don't miss this. Num plus equals to d. Why? Because we are jumping over multiples. So we have 2d, then we have 3d, then we have 4d, and so on. Every time we increment it by d, because we are running over multiples. So this is Sieve. What we have in, I mean, there is a lots of variations, lots of stuff you can do inside, lots of applications it has. But just remember this basic one. I mean, you don't need to learn or remember everyone, but just see that what we do is we just iterate over multiples of all the numbers. D from 2 to n, we just iterate over all multiples. Okay, so what do we have? I mean, inside the loop, what do we have? We have num is divisible by d. That is, we have num is divisible by d. So num is properly divisible by d. It's not that num is it's not that d can be 1 or d can be num, right? Because we have at least 2d. So num is properly, let's say properly divisible. Let's say properly divisible by d. So yeah, properly divisible, I mean it's not 1 and it's not equals to num. Yeah. So what does that tell us about num? That it's not prime, definitely. So it tells us that it is not prime. Is prime of num is equals to 0. There is lots of stuff it tells us about, like let's say that what about num? It says that I can say that we can, if you want to maintain a list for divisors, we can say that yeah, num, we insert d as a divisor, yeah, because it is one of the divisors. Another thing, if you want to maybe count divisors, you can say that divisors count of num plus plus. There's lots of things you can do inside. Yeah, we can say that d is one of the divisors of num. I mean, yeah, there are plenty of variations. So we were discussing about prime, so let's hang on to that. We will discuss some problems of it in later sessions. So let's stick to prime only. So is prime num is equals to 0? Sure. Let's call it false. Why? Because num is properly divisible by d, not 1, not num. It is properly divisible by d. We know that it can definitely not be prime. So we say that its prime is num. Oh yeah, I forgot to initialize them. I forgot to initialize them that everyone is a prime. I am assuming that everyone is a prime. So currently I am going to set them to true. Yeah. So currently I say that everyone is prime, and then I iterate over multiples and I say that you are not prime, and in the end, who are the two real primes, they can be they would be present. So let's see if this works or not. So oh yeah, I did not pass n. So Sieve basically this is receiving argument, like this is generally the maximum a number can go up to. Like in our case it was 10 power 7, I think. Yeah, where is it? Oh, so this is not there. Yeah, so it was up to 10 power 7. So we will pass 10 power 7. Sieve 10 power 7. 10 power 7. Cool. So let us make the array also is prime, right? Yeah, 10 power 7. Yeah, cool, it seems fine. So yeah, in 10. So what does this Sieve is? This, I mean, this version of Sieve, this is going to tell me that which of the numbers from 1 to n are prime and which are composite. For 1 you can see that I have not done anything, so let's keep it that way only. So let's see see out. Let's see whether Sieve is returning correct or not. Let's say 7 should be prime, 7 should be true. What about 77? It should not be prime. What about let's say 81 should be, let's see, some random stuff. Yeah, yeah, cool. And let's see, 816. Yeah, let's run this and see. Let's see if this compiles. There are some errors. Oh, I did use colon somewhere. Yeah, this. Yeah, let's remove this. This is not used currently, and yeah. Sieve. Oh, it's not Sieve. Oh, yeah. Oh yeah. It's is prime. Cool. Yeah. Sieve was a function. Sieve is the variable. Yeah, that's what I'm maintaining. Yeah, let's see. It says 10010. It says 10010. Is that correct? 7 is prime, true. 77 is not prime. That's correct. 7 and 11 divided. 81 not prime. 8167 is prime string. Yeah, I mean that was a random number, and getting it to be prime, the chances of that. But yeah, we got it. Yeah, 816 is not prime. Definitely, we can see 2 divides it. So yeah, seems like it's working. Yeah, so that is all. So basically this is the yeah, I mean the main thing yet to do is that I mean definitely this works, and yeah, this worked for 10 power 7 also. If you notice, this worked for 10 power 7 also. Let's see how much time did it take. Let's see. It took 1.05 seconds. Yeah, so yeah, it's around 1 second only, so that's good. Yeah, so I mean yeah, I mean of course there is one thing that you write the code and then you check it if it is passing time or not, but that's not usually a good way, of course. Yeah, so let us see how many operations does this usually do. So I mean you can do it by mathematical analysis, like how many operations are doing in each insider loop and outside loop, and yeah, that we can do that also. We can also do one thing, we can also simply do operations plus plus, because this is one of the operation, this is the innermost loop, and this is the this contributes to one operation. So this is one operation that I'm going to do. So I'm going to print here how many operations did I need. So let's see how much is this. This should be definitely less than 10 power 9.5. I mean it would be around 10 power 8, less than 10 power 8, because it completed in 1 second. So let's see. Oh, I did not compile, I guess. Yeah. It's this one. Nice. Let's see. How many operations is this? 1, 2, 3, 4, 5, 6, 7, 8. It's 1.4 E8 operations. Cool. So it's 1.4 E8. So looks like it should take around 1.4 seconds. Yeah. Based on the assumption above. Yeah, but 1 second seems fine. Yeah. So this is definitely less than 10 power 9.5. Yeah, but I mean we have to do time complexity analysis, because we cannot say for 10 power 7 my code gives 10 power 8 operations, for 10 power 6 it gives these many operations. You have to give in terms of the input, right? So let us analyze that mathematically also. So I mean this one is pretty simple, that of course, yeah, this is also simple. So what we are doing is, this is outside loop. When we are inside, we know that d is fixed for this iteration. D is fixed, and when we are inside that loop, we know that what we are doing is we are iterating over multiples of d, but we are limited by n. We are not going beyond n. So we know that how many numbers are multiples of d here. These are, we have d, we have 2d, we have 3d. Sorry, we don't have d. We have 2d, we have 3d, we have 4d, dot dot dot, up to maximum of n by d into d, right? N by d into d, because if we go beyond that, then we know that it is going to exceed n, and this loop would break. So how many operations for a fixed d do we have? 1 operation, 2 operation, 3 operation, 4 operation, and looks like around n by d order of operations. Okay, so let's write it. For given d, we have O of n by d operations. This is for a given d, and d is ranging from where to where? We have d ranging from 2 to n. So let's, I mean when we are discussing about time complexity, small cases 1, and these things don't matter. So let's say that, so we have overall complexity we have is O of n by d we have to sum it up for all D.